Let me announce the next lecture. Sorry for a small delay. Our speaker is Igors Garbovickis, and the title is Convergence of Renormalizations and Rigidity of Multicritical Circle Maps.
So thank you for the introduction, and thank you to the organizers for organizing such a wonderful event. It's my first conference in person quite some time, so I'm a little bit nervous. But I'm going to talk about convergence of renormalizations and rigidity of multicritical circle maps. This is joint work with Michael Yampolsky. Let me start by probably giving some explanation of several words from the title. So now I can. So first of all, we'll be talking about maps of the circle, and the rigidity problem in the context of circle maps goes back to Poincaré and Denjoy. So in particular, the Denjoy theorem says that if we have a smooth circle diffeomorphism whose derivative has bounded variation and the rotation number is irrational, then such a diffeomorphism is topologically conjugate to the rigid rotation. The rigid rotation by the rotation number, of course. So equivalently, we can say that the orbit of every point under the map F is dense on the circle. So, then the conjugacy to the rigid rotation is unique up to the initial choice, where, let's say, we take a point, we decide where this point is taken by the conjugacy, and that determines the conjugacy. The rigidity question in this context would be a rigidity problem for circle diffeomorphisms, would be the question, what can be said about the smoothness of the conjugacy? So in other words, can the conjugacy be better than just continuous? So it turns out that yes. So the celebrated Fermat's theorem, later improved by Yampolsky, says that if the circle diffeomorphism is sufficiently smooth, so, let's say of smoothness C3 or higher, and the rotation number satisfies the Diophantine condition, then F is C1 smoothly conjugate to the rigid rotation. So I'm not aiming here for the sharpest result, so just to give you a flavor of what can happen. So further improvements of this result were made by Heinz and I, Klinsky, so some related results were obtained as well. Maybe I would like to make just a couple of remarks. But first of all, the condition, first of all, the set of rotation numbers that satisfy the Diophantine condition has full Lebesgue measure. And second, if the Diophantine condition is not satisfied, Arnold showed that the conjugacy might not even be absolutely continuous. So in this setting, there is no hope for smoothness. In my talk, I will be interested in circle maps, but I will focus on not circle diffeomorphisms, but on maps of the circle with critical points, so-called critical or multicritical circle maps. So we may think of such maps being located on the boundary of the domain of diffeomorphisms, So if you move towards the boundary of the domain of diffeomorphisms, you might in the image get a critical point or several critical points. So in the case of a single critical point, such maps are called just critical circle maps. If you have more than one critical point, we'll call them multi-critical circle maps. So in the case of a single critical point, I would say the definition here is on the slide. So a CR smooth critical circle map is an orientation preserving CR smooth homeomorphism of the circle with a single critical point. And we would like the critical point to satisfy the so-called power law. So locally around the critical point, it looks like a power map. So a map x to the power d. So in other words, there exists local diffeomorphisms phi and psi, which you put around the power map. And the smoothness of phi and psi is the same as the smoothness of the critical circle map, so is CR. Similarly, you can consider critical circle maps of various other classes, say C infinity or analytic. So D will be called the critical exponent. Since a lot of the methods are analytic, we restrict for D being an odd integer. So we'll see later where this appears. And a version of Denjoy theorem for critical circle maps was proven by Igors. And it says that if we have a critical circle map with an irrational rotation number, then the orbit of any point on the circle is dense under the dynamics of such a map. So in other words, this means that this map would be continuously conjugate to a rigid rotation. But the existence of a critical point means that there's no hope for such a conjugacy to be better than just continuous. Then it makes sense not to conjugate with rigid rotation, but take two critical circle maps with the same rotation number and consider a conjugacy between those two, which takes a critical point to a critical point. And then we can state Igors' theorem, or a version of Denjoy's theorem for critical circle maps as follows: that two critical circle maps with the same irrational rotation number are topologically, well, in fact, quasi-symmetrically conjugate. And then for such a conjugacy, one can ask the rigidity problem. The rigidity problem would be, is this conjugacy smooth? And if yes, then of what smoothness? And so let me postpone detailed answer, so short answer. So yes, it will be smooth. Let me postpone the detailed answer and instead focus on, or state the same question for multicritical circle maps. So the same question if we have several critical points. So all critical points are exactly of the same type, well, of a similar type as in the case of critical circle maps. So they are of power type. Before passing to the discussion of the rigidity problem for multicritical circle maps, we need to discuss combinatorics. So in the case of a single critical point, the rotation number essentially defines the combinatorics in the sense that If we look at the orbit of the critical point, the rotation number tells us the relative position of the points in the critical orbit. But if we have several critical points, then the combinatorics is more complicated, and we need to describe. So here F will be a multicritical circle map with an irrational rotation number. And then by Yakoz's theorem, F is continuously conjugate to the rigid rotation. So we want to somehow relate the positions of the critical points, and it makes sense to do it via the invariant, the unique F invariant ergodic measure that is obtained as a pullback of the Lebesgue measure on the circle, so via the conjugacy. This measure is independent on the choice of the conjugacy. So the conjugacies all are the same up to the rotation, up to rigid rotation. So the measure mu F is independent on that choice, and essentially defines the combinatorial distance between points on the circle. And then we can combine all combinatorial information about a multicritical circle map. And well, we denote, well, we call it a signature of F. So a marked signature of F with respect to its critical point C. So we choose a critical point, and the marked signature with respect to that critical point is the following combinatorial data. So first of all, of course, we need to keep the rotation number. We need to know how many critical points we have. So N capital is the number of critical points. We enumerate them, say, in the counterclockwise direction. Essentially, the choice is arbitrary, but well, we have to make a choice. So we enumerate them in the counterclockwise direction, starting from the critical point C. We need to know the critical exponents of each point. So dj are the critical exponents, and delta j will be that combinatorial distance between two consecutive critical points. Or in other words, mu f of the interval from Cj to Cj plus 1. And of course, since we're on the circle, it's natural to assume that the last one, Cn, is equal to C0, which is the critical point C. So this information, this signature, this marked signature, encodes essentially all of the combinatorial information about the multicritical circle map. And then if two multicritical circle maps have the same signature, well, with respect to some critical points, then there will be a conjugacy that takes, well, between the two multicritical circle maps, it takes critical points to critical points. And the theorem by Clark, Van Strien, and Trejo, and then independently also proved by Esteves and De Faria using different methods, says that such a conjugacy is quasi-symmetric. So our main result is the following, that if, in addition to that, we know that the rotation number of these two multicritical circle maps is of bounded type, then that conjugacy is not just quasi-symmetric, it's actually C1 plus alpha smooth. Let me make a few remarks. So first of all, what do we mean by bounded type? So the rotation number is of bounded type if, well, we take the rotation number expanded in the continued as a continued fraction. So R0, R1, and so on are digits, are the digits of the continued fraction. And if they're bounded, then we say that the rotation number is of bounded type, or if we know that it's bounded by some number b, we say that it's a bound of type bounded by b, and this is equivalent to a version of the Fontane condition. I can pointer this way, please. So this is the Fontane condition with power 2 in the denominator. The second remark is that so alpha is positive, so we have the conjugacy is C1 plus alpha smooth. Alpha is positive and depends only on the bound B and the so what we call the total criticality, or the product of the criticalities of all critical points. Let me say a few words about previous results. So this topic, the rigidity problem, has been studied, well, essentially completely solved in the case of one critical point, so in the case of critical circle maps. So the first result was due to De Fourier, De Mello, and independently Yampolsky, so in the end of 1990s, and they proved C1 plus alpha rigidity for analytic maps with a single critical point of criticality 3. So then for an arbitrary criticality, the proof was given by Esteves in her thesis and by Yampolsky independently at the same time. Essentially the only missing part compared to the previous results was the construction of the so-called rigid family. So a family of analytic maps of the cylinder, the cylinder C mod Z, such that if we have another analytic map of the cylinder that's topologically conjugate to map from that family, then that map is in that family as well. So this step was done by Esteves and Yampolsky independently in 2017. So another direction was to generalize these results from analytic maps to smooth maps. And that was done by Guarino and De Mello. So they used asymptotically homomorphic extensions to generalize the results to C3 smooth maps. Together with Yampolsky, we also obtained results for analytic, the rigid, C1 plus alpha rigidity for analytic maps with the critical exponent close to odd integers. So we say analytic, of course, at the critical point. Such maps are not analytic. They have branching at the critical point, but we mean that they are analytic everywhere else. This is in the case of a single critical point. In the case of two critical points, Yampolsky has shown C1 plus alpha rigidity for bicubic multicritical circle maps. So with two critical points, both of cubic type. And again, the proof was based on finding a rigid family. So apparently a rigid family suitable for that result was already constructed in previous works of Zachary. But up to now, the general case with an arbitrary number of critical points of arbitrary critical exponents was open. So finally, a remark about an unbounded type. So when the rotation number is an unbounded type, so all previous remarks were related to bounded type. In case of unbounded type, there's really no hope to have C1 plus alpha rigidity. So there was a counterexample constructed by Avila that if the rotation number is unbounded, there could be examples to critical circle maps analytic, which are only C1, for which the conjugacy is only C1. And Hyman and Ceplinsky showed that actually exponential convergence of renormalizations in C2 metric implies that the conjugacy is C1. So here so the word renormalization appeared in the previous talk. So, but nevertheless, I was also planning to give some explanation of what it is. So, in general, we can view renormalization as a rescaled first return map to a subset. So if we have a dynamical system F, as in the picture, we may choose a subset of the domain, so this small piece, and consider, so if we're lucky, then the first return map on this subset is defined. And then we would like to rescale this subset to the size of the original domain. And we obtain another dynamical system, which we call the renormalization of F. Renormalization has lots of applications. And as you see, naturally, in particular, it could be used to detect various kinds of self-similarities. So let me state several empirical rules. I deliberately avoid giving precise formulations because in different cases that could be, well, the feelings would be quite different and proved quite differently. But some empirical rules are could be the following. That, for example, if we have an invariant set, the green piece in my picture would be an invariant set, and so I will refer to the picture. And if we are very lucky and the renormalization of F is the map F itself, then we see that there is some self-similarity in the invariant set. Of course, that's a luck if the renormalization of F is F itself. So, but we can still be happy if the renormalization of a map is renormalizable again. And if we can do this infinitely many times, then we can treat the renormalization as a dynamical system on the space of dynamical systems. And if, again, we're lucky and we take F and we renormalize it and the renormalizations converge to some F0, then we may say that the invariant set is asymptotically self-similar. Or if we have two different dynamical systems, F and G, as here, then if it turns out that the renormalizations of these two dynamical systems converge to each other, then we may say that, so we may conclude that F and G have the same, or asymptotically, the same small scale structure. And this is what we need in order to determine smoothness of the conjugacy. So those were some empirical statements, but a precise statement in terms of renormalization that's equivalent to the rigidity, C1 plus alpha rigidity for multicritical circle maps, is the following. Just we will always place one of the critical points at 0 for convenience. And we will always consider a marked critical, so a marked signature with respect to that critical point. So the theorem is that for any 2C3 smooth multicritical circle maps F and G with the same signature and the same irrational rotation number of bounded type, the C0 distance between their renormalizations converges to 0 exponentially fast as n goes to infinity. So at this point, so this result is this result will imply C1 plus alpha rigidity, and at this point I should talk about how we renormalize circle maps. So this picture intends to illustrate the renormalization of, well, either critical circle maps or multicritical circle maps. So if we have a critical or multicritical circle map F, as always, we decompose the rotation number into a continued fraction, and we can consider the so-called nth convergence of the continued fraction just simply by removing the tail of the continued fraction. In the irreducible form, it's represented as a fraction Pn over Qn, and the numbers Qn will give the first return time times for the picture here. So we consider the interval from that contains 0, the interval in the circle that contains 0. So on one side of that of 0 we'll have Fqn plus 1 of 0. On the other side, Fqn of 0. And the first return map of that interval, the union of red and green, would be a piecewise defined map. So on the green interval, it will be Fqn, and on the red interval, it will be Fqn. On the green one, it will be Fqn plus 1. And so that's the first return map. And as we discussed, the renormalization is a affine rescaling of that. So the renormalization of F will be the rescaling of such a piecewise defined map, where the rescaling takes Fqn of 0 to 1. So it's a little bit unfortunate, or looks unfortunate, that we start with renormalizing a circle map, and we get a map of an interval. So it's tempting to glue this interval into a circle, and one could use, let's say, the red map as a gluing map to glue the interval into a circle. But then the problem is, well, and again, then we will get a map of the circle, of a circle with a critical point or several critical points. But the problem is that this circle would be, well, it would be a smooth manifold, diffeomorphic to a circle, but without a canonical affine structure. So we will actually get a conjugacy class of circle maps as a result of the gluing. But this is not exactly what we want. We want to have a single map. This is why in the classical theory, people don't do the gluing and just consider the maps of the interval. And then if we do that, then it makes sense to figure out how one can renormalize. Well, okay, so such maps of the interval are called commuting pairs. So in the case of a one critical point, it would be critical commuting pairs. In the case of several, it would be multicritical. So they obviously by the construction, the two maps, the green and the red one, they will commute around 0. And it makes sense to learn how to renormalize, starting not with a circle, but renormalize a commuting pair. And the picture would be the following: that if so, we take the red map, we iterate it once, and then iterate it along the green interval until the red interval would cover 0. And then we simply remove, in this picture, we simply remove everything which is to the right, and we will obtain a new commuting pair. So the red interval will be taken into this red interval, and the part of the green interval will be taken wherever by the same map eta. So that would be a normalization in the language of commuting pairs. And again, we do the rescaling as always. So now let me talk a little bit about the ingredients of the proof. The first step would be, well, as I mentioned somewhere, of course, we are going to apply analytic methods. And so the first step would be, if we start with an analytic map, we can say that sufficiently high renormalizations of an analytic map extend to the so-called holomorphic commuting pairs, which are analogs of polynomial-like maps. And those have definite moduli. So this was, in the case of a single critical point, it was shown by Yampolsky in the late 1990s. And in the case of several critical points, the proof was adapted recently by Esteves, Simani, and Yampolsky. And so the picture illustrates what a holomorphic commuting pair is. So it's an analog of polynomial-like maps, although maybe does not look exactly as polynomial-like maps. So we have an outer domain, which is the range of the holomorphic commuting pair. And we have 3 maps, each defined on its own domain. So these are the wings of the butterfly and the central domain here. And on each of these domains, the corresponding map, it's psi here, eta here, and the composition psi composed with eta in the central domain. They're taken, they are branched coverings onto the larger domain with some slits along the real line. So for each map, the slits will be different. So complex bounds say that if we normalize our map on the analytic map on the interval sufficiently many times, then such a extension to homomorphic commuting pair exists, and the modulus of the homomorphic pair is bounded away from 0. So the modulus is, well, essentially is the difference between the union of the 3 domains in the center, and so the modulus of the annulus that separates the 3 interior domains from the boundary of the outer domain. So there is some important difference compared to the case of a single critical point. In the case of several critical points, there are, so the homomorphic commuting pair will have critical points not just on the real line, but also somewhere in the complex part of the picture. Those critical points are unavoidable, and they cause some technical difficulties. But once we have a homomorphic commuting pair, we can use the strategy similar to the one with polynomial-like maps. So we can iterate a homomorphic commuting pair. In particular, we can talk about escaping points and non-escaping points. So the set of non-escaping points will be called the Filgilia set. We can also renormalize a homomorphic commuting pair. So renormalization of homomorphic commuting pair will also be a homomorphic commuting pair. So you can think of this as zooming into the center, and then appropriate iterates of the homomorphic pair would be smaller bow ties similar to this one. And also we can apply the pullback algorithm. So we can do the pullback, and if we have 2 homomorphic pairs with the same combinatorics, or maybe better to say topologically conjugate, then we can extend the quasi-symmetric conjugacy on the real line to a quasi-conformal conjugacy of the 2 homomorphic pairs. So here there's again a difference compared to the case of a single critical point. In the case of a single critical point, we may say that if the 2 critical critical commuting pairs, so the maps on the real line have the same combinatorics, so same rotation number, then their homomorphic extensions are always topologically conjugate, and then the quasi-symmetric conjugacy is promoted to quasi-conformal conjugacy. But in the case of several critical points, the existence of critical points, complex critical points, actually, it could happen due to those complex critical points that the map on the real line is quasi-symmetrically conjugate, but the complex extensions are not topologically conjugate. So the right statement here would be that if the maps on the real line are have the same combinatorics, then after renormalizing sufficiently many times, they will have the same combinatorics. Well, the homomorphic extensions will have the same combinatorics, and then the pullback method would work. And then, so we can promote the quasi-symmetric conjugacy to quasi-conformal conjugacy only after doing sufficiently many renormalizations. So now, how can we prove convergence of renormalizations or C1 plus alpha rigidity? So the idea goes back. So in our work, we use a theorem of Macmullen, a general theorem, which I prefer not to state right now. The statement is rather complicated, but instead, let me try to give a flavor of the approach. So once we have the quasi-conformal conjugacy between two holomorphic pairs, if we are very lucky, yes, so if we have such a quasi-conformal conjugacy, then it means that we have an invariant Beltrami differential on a holomorphic pair, or even we can say an invariant line field in this case. And if we are very lucky, then this invariant line field is actually trivial, and then the corresponding conjugacy is holomorphic. And then as you zoom into the center, the holomorphic conjugacy becomes closer and closer to just an affine conjugacy, and that's equivalent to convergence of renormalizations and actually equivalent to the corresponding rigidity statement. But of course, we cannot expect to be so lucky that there is no non-trivial invariant line field on a holomorphic pair. Our goal is to show that actually the field Julia set admits no non-trivial invariant line field, but for the complement of the field Julia set, one can show that 0 is the so-called delta D point of the field Julia set. So in other words, for every radius r, the largest disk contained in the disk of radius r centered around 0 and not overlapping with the non-escaping set has a radius smaller than r to the power 1 plus delta. So this is one of the explicitly stated ingredients of Macmullen's theorem, and together with point 1 and point 2, this would imply that even though there could be, of course, a non-trivial invariant line field, as we zoom into the center, the corresponding conjugacy will be C1 plus alpha conformal. So that's precisely what we need. So how much time do I have? I think I started a little later. So 5 minutes. Okay. So maybe I would like to give some proofs, maybe some short proofs in the end. One of the steps in showing that the non-escaping set admits no non-trivial invariant line fields would be to show that the non-escaping set has empty interior, in the case of several critical points, the proof is a little bit different from the cases with a single critical point. And again, the problem comes from the fact that if, well, again, as I already mentioned, the conjugacy on the real line does not imply the topological conjugacy of the complex extensions. So in order to get the topological conjugacy of the complex extensions, we need to renormalize more. And then the renormalizations would be conjugate for the complex extensions. So let me give a sketch of the proof. First we show that there are no periodic components. So the filled Denjoy set does not have periodic components. And the idea is to use, so the idea is quite a standard in this case, to use expansion of hyperbolic metric. So we take hyperbolic metric on this, well, delta is this large domain, so delta minus R. And one can show that due to expansion of the hyperbolic metric, so if we have a connected component of the interior of the Denjoy set, and we take a point in that connected component, then the iterates of that point converge to the real line. And then the dynamics on the real line is has no, so on the real line we have no periodic points. So this rules out the possibility of having periodic components. But of course, there's still a question of wandering components. So in order to show that there are no wandering components, we have to work a little harder. So of course, we know that the rational map has no wandering components. Well, due to the famous theorem by Sullivan. And we want to use that. So first step, we want to construct Blaschke fractions with an arbitrary signature. So Blaschke fractions would be, would take a unit circle to a unit circle. And apparently, even that step turned out to be somewhat complicated in the general case. So constructing Blaschke products with an arbitrary signature, in particular, taking care that the pairwise distances between the critical points are all realizable. Then, if we renormalize such a Blaschke fraction, of course, we get homomorphic pairs without wandering components. So in the multicritical case, that would be the end, because we take an arbitrary, sorry, in a single critical, in the case of a single critical point, that would be the end. We would have to just take, well, we take our homomorphic pair with the same real combinatorics as the one obtained from the Blaschke fraction, and just take a topological conjugacy between them, and that's it. But here we do not necessarily have a topological conjugacy. So we get a topological conjugacy only after we renormalize several times. So we get that for sufficiently large n, the renormalization, so I write re-renormalization, meaning that renormalization before rescaling. So renormalization of the pair H, which I denote by Hn, has no wandering components. But this does not necessarily mean so far that the map H does not have wandering components, because the pieces of the wandering components, so the wandering components can be away from the domain of the pair Hn, or they could intersect the domain and turn out to be escaping components for Hn, but wandering components for H. So if H has a wandering component U, then actually we can use the convergence. So this statement here, that the iterates of that point converge to the real line, and then after iterating a point Z sufficiently many times, we will get a point Zk, which will be sufficiently close to the real line. It will be in the domain of the homomorphic pair Hk, which is somewhere very, very close around 0. Then, since it's close to the real line, the dynamics of that point Zk under Hn, this small holomorphic pair will be governed by dynamics on the real line. So ZK will be non-escaping, but if it's non-escaping, it lies in the Phil-Julia set of Hn, but then it has to lie in the Phil-Julia set of H, and that will be a contradiction. So that's one of the steps in the proof for the well, non-existence of non-trivial line fields on the Phil-Julia set. And maybe just very quickly, let me say just a couple of words about how we pass from analytic case to C3 smooth case. So so once we establish the convergence of renormalizations in the analytic case, then well, in the C3 smooth case, we consider the so-called almost commuting pairs. So everything is the same except that the two maps do not commute, but they commute up to an order K, or well, probably better to say so that this is condition 3. The commutator, so if K is the critical exponent at 0, the commutator is O small of x to the power K. So why do we need almost commuting pairs? We can use the so-called shuffling lemma, which is an analog of the shuffling lemma by Sullivan used for unimodal maps. And if so an adaptation of the shuffling lemma here would be so if we are at a deep renormalization, then on each small interval we can approximate a smooth map by an analytic map, and then estimate the that this will not change the map, the composition too much, and this would show convergence of smooth renormalizations of smooth maps to analytic maps. But the problem is, which is not a problem in the model case, but here it is a problem, that by such approximations we will destroy the commutation condition. So the commutation condition will be instead just this almost commuting condition, so the condition 3. Then we show that actually, as we renormalize, the commutator of the renormalizations converges to 0 uniformly, and actually I did not write, it should be exponentially as well. The proof of that lemma is essentially just the real bounds. I can probably show this last slide, but let me stop here because I think I'm going over time.
Thank you. Do you have questions? Yeah, yes.
Kind of wider or general. The other is very simple and specific. Maybe I got something wrong, but you said that finally the statement depends on the product of criticalities. So I would like to ask about those complex critical points. Maybe I'm completely wrong, because and it's hidden in the product, but I suppose you need some bounds on the geometry of those complex criticals, because if they come, not that are just deep inside the wings you draw, but they cannot come too close together, because in the limit they could finally be glued.
So let me try to answer the question. So I did not really say where the complex critical points come from. I just said that they are unavoidable, and they are. So let me show the picture. let me explain where we get complex critical points. So if you have several critical points on the circle or on the real line, as you renormalize, you take a small, let's say, a small interval adjacent to 0, and you start iterating. So at some point, so you get a sequence of those intervals, so the orbit of that interval, and at some point you get a critical point on that interval. So having a critical point on that interval means that then after when you go to the next interval, not just this interval is mapped to the next one, but also there will be complex curves, which are curves in the complex domain, which are taken to the real line. If we have if we have a single critical point, or even if we have just 2 critical points, this would not be an issue. But if you have a lot of critical points, then after that, as you keep iterating this interval further, you can land on another critical point. So if you pull this picture back, this means that you will have a critical point in the complex domain, which first was taken on the real. So you will have a point in the complex domain, which was first taken on the real line. And after that, it was taken onto some other critical point on the real line. And then iterated further. And so your normalization is the composition of all of those iterates once your small interval comes back to 0, and then rescaling. So this way you got a critical point somewhere in the complex domain, but that critical point is mapped by the first iterate. That critical point is mapped onto the real line. So this means that even though you get complex critical points, they are reasonably nice because they are taken onto the real line. But the problem is that the topological picture of the complex extensions can be different. But then if you take a sufficiently deeper normalization, so your intervals are very small, you will be iterating this small interval together with a small neighborhood of that, and it will jump all over the place along the real line before it comes back. If this interval is sufficiently small, then you will collect at each step no more than 1 critical point on the real line. You will not collect any critical points which are in the complex domain. So this sequence will have. So in other words, after you come back, you of course will have, after you renormalize, you will have critical points in the complex domain, but the structure of this set, which is taken to the real line, will be determined completely by the combinatorics on the real line. So, and this is why, after sufficiently many renormalizations, the topological structure of the complex extensions will be the same for 2 maps with the same real combinatorics. So that somehow turns out to be not an issue.
Okay, I think more detailed discussion will be done later. I think we have some online questions. Do we have? Leticia doesn't do. Yes. Okay, so no more neither inside or online questions. Then let's make a break. Thank you again, speaker. And as it's only 2 minutes left for the coffee break, I think we shall extend it by 10 minutes. So